Hiya 12, we've got a slightly lower tech version of the video for you today. Having done your mock and everything, we had got to the end of looking at rates. So with our Arrhenius equation we have finished the rate section of Module 5. We're going back in a way to have a look at KC, although I did teach you a couple of the bits that we need to know for KC anyway, but it is the equilibrium constant that we learnt about earlier in the year. There are a couple of additional things that we need to know though, and that is about homogeneous and heterogeneous equilibria. Homogeneous, well, we know homo means the same, so this is where all species are in the same phase. For example, they're all gases, or they're all dissolved solutions. Yeah. So if we had an example of, for example, nitrogen gas reacting with hydrogen, as in the Haber process, to produce ammonia and H3, we got a gas, we got a gas, we got 2, and we got 3. This is a homogeneous equilibrium because everything is in the same phase, everything is a gas. Similarly, if everything was aqueous, that would be homogeneous equilibrium as well. If we have a heterogeneous equilibrium, then that's where we've got a mixture of states, a mixture of phases. So if we had so as an example, if we took carbon, which is a solid, reacting with H2O gas to form carbon monoxide, which of course is a gas, and some hydrogen, which is of course gas. This is heterogeneous because of course we've got a solid and then we've got gases. Now the thing where we've got heterogeneous equilibria is that we are only interested in the gases and the aqueous components, because essentially the concentration of our carbon isn't going to change because concentrations of solids doesn't really make sense. Similarly, if we had a liquid, the concentration of that effectively stays the same. So when we're dealing with these, we're only interested in the gaseous species or the aqueous species like this. Just to remind you as well, because I did teach you for the bit where we were learning about it, but if we take, for example, these, so N2, 3H2 going to NH3, or gas, or gas, gas. We were hopefully confident with writing the KC expression, so of course it is products divided by reactants, and it's each species raised to the power that there are in the equation. So we'd have NH3 squared, the concentration of N2, and the concentration of H2 cubed. And here, because we're not interested in the solids, so if we had our equation here, then we again have product over reactants, each to the power that it's in the expression, in the equation, but of course we're not interested in the carbon, so we actually end up with carbon monoxide gas multiplied by hydrogen gas, square brackets, divided by the concentration of H2O, which was gas in this case. Okay, and the thing that they've added at this point as new for you guys, as new for you guys, because I taught it to you, was working out the units for this, because that's not something they expect you to do for AS, but it is something they expect you to do for A2. So we've got, of course, the units of concentration, mole per decimeter cubed, and we've got that squared on the top, and then we've got moles per decimeter cubed times by moles per decimeter cubed. So we're cancelling things out. So this cancels out one of those, and one of these cancels out this. So we're now at 1 over moles per decimeter cubed squared, which becomes, let's give ourselves a little bit more space. That is 1 over moles squared decimeters to the power 6, and of course we want, right, I need to put minuses on those. Of course we need to swap the signs when we take it from the bottom to the top, so we're going to end up with decimeters to the power 6, moles to the minus 2, or of course moles to the minus 2 decimeters to the power 6. Those are the same thing, so we have either one of those, either's fine, doesn't actually matter which order you put it in. The mark scheme will normally specify it with the positive indices first, the negative indices second, but fundamentally it doesn't matter. And we'd do the same thing over here. So we're going to have moles per decimeter cubed, moles per decimeter cubed divided by moles per decimeter cubed. So we'll cancel one of each out, and that handily leaves us with moles per decimeter cubed. Okay, so at that point, fundamentally nothing's really changed. Now, the biggest change that we will experience is how they're asking the questions. So the way that we have had it before is when they give you the question, they will give you the equilibrium concentrations of things. Now, that of course makes it nice and easy, because so long as you can work out what the KC expression is, then you don't really have much to do in terms of working out what anything else is. It's done for you. For A2, of course, they're going to push you a little bit more, and they're going to expect you to be able to work out the equilibrium concentrations of things. And that is a bit more complicated, and there's a lot of ways that they can ask you this. Okay, so I've got an example here. So a sample of, you can't see the decimal points very well on there. So we've got, as an example question, a sample of 1.60 moles of nitrogen oxide are reacted with 1.40 moles of oxygen in a chamber with a volume of 4 decimeters cubed. We'll probably say that it keeps constant volume as well. At equilibrium, the mixture contains 1.20 moles of nitrogen dioxide, and the equilibrium that we've got is the equilibrium there. So what we want to use is a way of working it out. So I use, as you'll see it in all sorts of places, rice. So we have the reactant, we have the initial, we have the change, and then we have the equilibrium. Now, depending on what information you get given, you're probably going to work all of this out in moles, which means that at the end, effectively, you want to have a concentration at equilibrium situation. Okay, so we're going to whack in 2NO plus O2 in equilibrium with 2NO2. Okay, And I'm not worrying here about the fact that they're all gases, because they're all gases. Okay, so in our reaction, we're interested in the fact that it's 2 to 1 to 2. Okay, and our initial numbers of moles in this case, well, we've been told 2 of them. So we've been told up here that we're putting into our sample container 1.60 moles of nitrogen oxide, so 1.60, and we're told we're putting in 1.40 moles of oxygen. Because we've not been told that we've put any nitrogen dioxide in, it's a reasonable expectation that we've not put any in. So we're starting with no moles of the nitrogen dioxide. Okay. Now, they can tell you these bits of information in a wide variety of ways. So they could tell you that once they reach equilibrium, 90% of the nitrogen dioxide has been consumed or has reacted. Yeah. Similarly, they could tell you that about the oxygen. They could tell you the number of moles of one of these reactants at equilibrium. So they could tell you, I don't know, that there's 0.2 moles of nitrogen oxide remaining. That would be fine. Or they can tell you the number of moles of, for example, our product that we've got, or how that's changed as well. Okay, so here they have told us that at equilibrium, so if we add a couple of lines onto our table, just to make our life a little bit easier, ignoring the fact that I went through one of my chemicals there, we have been told this box here. We have been told what the equilibrium number of moles of this is, and this is 1.20. Okay? Let's get that out of the way. That means that the change in moles of this, so I'll leave those bits as being the bits that the question has told us. That means that this has gone up by 1.20 moles. Okay? We now need to know how many moles of nitrogen oxide and oxygen are remaining. To do that, we're going to use the stoichiometry. So we know that the ratio between nitrogen dioxide and oxygen is 2 to 1. So that means however much of this we've made, we've used half as much of this. So this is going to have gone down by a half of 1.20, so down by 0.60. Okay, so we'll just do the maths. 1.40 minus 0.60 gives us 0.80 moles remaining. And then this is 2 to 2 between the nitrogen dioxide and the nitrogen oxide. So that means that it's effectively 1 to 1. So this is going to have gone down by 1.20. Okay, so 1.60 take away 1.20 gives us 0.40 moles. Okay. We can't just shove that into the equilibrium expression yet, because these are numbers of moles, so we need to work out the concentrations, and this is where the fact that we were told that we were doing it in a container which is 4 decimeters cubed is important, because of course concentration is moles per decimeter cubed. So to do our calculation, we're going to do 0.40 divided by 4, which is 0.1. We're going to do 0.80 divided by 4, which is 0.2, and we're going to go to 1.20 divided by 4, which is 0.3. Okay. Now we can shove it into our Kc expression, but first we have to write our Kc expression. So we've got Kc is equal to concentration of nitrogen dioxide squared divided by the concentration of nitrogen oxide squared multiplied by the concentration of oxygen, not squared. So if we substitute in our numbers, we've got 0.3 squared, 0.1 squared times by 0.2, which gives us, at the end of the day, an answer of 45. We need to know the units as well. So if we, let's see, where did my pink pen go? I'll do it in black. So if we do our units, then we've got moles, per decimeter cubed. Actually, let's do it here. So we've got moles per decimeter cubed squared divided by moles per decimeter cubed squared multiplied by moles per decimeter cubed. We'll cancel out what can cancel out, so the squareds can cancel out with those, giving us 1 over moles per decimeter cubed, which gives us decimeters cubed per mole. Or moles to the minus 1 decimeters cubed. Okay. So this is the fundamental change. Okay. Now, additionally, if one of these substances had been a solid or a liquid, we wouldn't be including that in our Kc expression. But this is the way they've made it harder. They've effectively made it so that rather than just giving you the equilibrium concentrations, you have to work them out. This is the easiest way of doing it most of the time. There are some situations where they've given you it in a really peculiar format, but sort of fundamentally we need to get to this line here. We need to get to our equilibrium concentrations. The way that we do that is partly up to you, but this is the easiest way if you're given an initial concentration or initial number of moles. If you're given initial concentrations, then we'd have to have some situation where the volume didn't change, which is, to be honest, what we normally have. At which point you could, in theory, do all of your calculations with concentrations, because you're doing it in a container that doesn't change in size. But most of the time they give you the values as numbers of moles. Okay, I'm going to add in a bunch of questions which are looking at working out Kc using A2 type stuff. That's what I'm going to leave you with for the rest of this week. And I'll make a video going through all of those, which will hopefully address any problems that you have. Okay, good luck, guys.